Part E.2, recursion tree method. So we continue the second part of the topic selection problem and recursion tree method. So we didn't finish in part D. So the second half of that. All right. So hope you can still remember the first half. Yeah. So we are at this point. Yeah. So we use the 3-element partition. So remember the 3-element partition, we divided all the elements of the given array into 3-element groups. Okay? Things like that. Okay? All right. So then we find medians of all the groups. So then we get a median of the median, M star, the median of all these medians. Okay? So then we use that element as the partition element. Okay? Here, in place, partition element. So then we do the partition. All right? So that's the story. So we inherit from the first half. Next, so let's continue. Now, we need to estimate the cost. So here we use a function, represent the cost. For this selection problem, so we use S. S, the cost function of the selection problem for problem size n, S of n. So we want to estimate this function. To do that, so let's do some analysis first. So we want to set up a recursive inequality for estimation. It's inequality, so not equality, inequality, but estimated inequality in a recurrence way. Recurrence way. Because in our algorithm, we call the recursive function many, many times. So we have that recurrence in our estimate. So let's start at the left-hand side. So that is our goal, our estimation goal, S of n, less than or equal. Why less than or equal? Because at the right-hand side, we use the worst case. Worst case. Okay? Yeah. So when we do estimate, so we try to be a little more generous. Okay? So we consider the worst case, each step, the highest possible cost to be used. So in that way, so we can cover all the possibilities. Otherwise, if you do not consider the worst case, you may not cover some of the special cases. All right, so with that in mind, so let's do step-by-step estimation. Let us do the cost breakdown, term by term, okay? Step by step. The first step, find the R medians. We need to pay some cost, right? So what is the cost to find R medians for R groups? So that's easy. So how much is it? That's easy. N. So why N? The problem size N? Because, remember, for convenience, we choose N equals 3R. Okay? For convenience, we choose that number. Okay? All right. So then there are R groups. Okay? Each group, to find a median, how many comparisons do we need? 3. Okay? Yeah. Remember, so that is one of your homework assignment questions. 3 comparisons. Each group we use 3 comparisons, but you have R groups. So you need to use R times 3, 3R, that is N. Okay? So the first term, so let us put it back to our estimate inequality, n plus, the second term. Then, after that, we need to do 2s on comparisons. 2s, why 2s? Because this part is unknown. Part 1, we know, so look at the part 1. Part 1, all the elements in part 1, we know the relationship of each element with m star, median of the medians. We know that relationship, less than, less than, we know that. For part 2, we also know that the relationship, each element in part 2 greater than. All right, so you need to recall the steps we did last time. So here I do not want to repeat that. Too long. The story is too long, so I do not repeat that part of the story. No. All right, but this middle part, the relationship unknown, greater than, less than, nobody knows. For that reason, we need to do more comparisons. How many more? 2s more comparisons. Okay? All right. So that cost, how much is the cost? This many compared 2s. So what is that? 2s approximately equal to n over 3. So y approximately equal. So remember, we assume r equals 2s plus 1, right? So that's our assumption, also for convenience. Okay? So 2s approximately equal to r, right? Difference is just 1. Okay? 2s approximately equal to r approximately equal to n over 3. Okay? From here. So you can see, so this is our second term estimate, n over 3. All right, the third term, now recursive function call. The third term, we need to find the median of the R medians. So that is a smaller selection problem. So recursive function call. Okay? So what is the cost? It depends on the size. The size is R. R is 1/3 of n. So you know the cost of that recursive function call is s of n over 3. So we add it to the inequality. Finally, the last term we need to estimate. Finally, elimination, right? Then, after we finish the partition step, we need to eliminate some part of the elements. So after elimination, we have a subproblem left. So we need to solve that subproblem. But to solve that subproblem, we need to know approximately what is the problem size of it. Okay? All right. So here you can see from this diagram here, if we do elimination, we consider the worst case, not the best case. Okay? All right. So the worst case is we can eliminate part 1 if we know, because we know m star greater than. So we can, so based on, based on the k value. Based on the k value. So the k value is known. The rank of m star is known, right? Rank of m star is known. In place, that number is known. So you compare k with the rank less than, greater than, so you know which side you should eliminate, either part A or part B. You know which side you should eliminate, but only one of the two sides. Okay? But for the either side, you can only eliminate one block of it. One block. Okay? For the worst case, what's the worst case? The minimum number of elements you can eliminate, that's the worst case. The more elements you can eliminate, it's better, right? Yeah, you can do better. But now we try to be, mainly worry about the worst case. Yeah. So we try to think about the minimum number of elements that can be eliminated. So that either part A or part B, that's 2s plus 1. So the remaining part, 4s something, right? 4s something. So that is 2n over 3, the size 2n over 3. Yeah. Try to figure out, try to look at from a picture. Yeah. And only consider the worst case. So you will get, because later we don't want to use our expression using s or r. We want to use the original size n. Yeah. So for that reason, you can see the size representation 2n over 3. Yeah. So then we put it back to our inequality. So you can see that is our recursive inequality. So we can use it to estimate our cost function s of n. Yeah. But we need an initial condition, so that's easy. S of 0 equals 0, s of 1 equals 1. Okay? And we can simplify the recursive inequality in this way. Okay? Yeah. Slightly simpler. Yeah. So our next step, solve this recursive inequality. Solve it. Okay. Yeah. Now, we try to find a solution. Yeah. But to solve it mathematically, it may not be that easy. The reason is, how do you handle fractions as the parameters of recursive functions? How do you handle that? Okay? You may like to make integer, right? The problem size integer, so that will be very complicated. Yeah. So if we want to use math to solve this recursive inequality rigorously, it is very complicated. So probably nobody can do it. Yeah. So I think nobody can do it rigorously. Yeah. So that's why we try to make it a little easier. We use some reasonable estimate. We will do estimate, but pretty reasonable. Yeah. So in computer science, we always do estimation like this, reasonable estimate. So not very precise, but good enough. So that's the common way we use. Yeah. So it's quite different from people solve problems in math. Yeah. All right, so let's look at the estimate. Here we will use a new method. So this method is called recursion tree method. We will draw a tree. So we visualize the whole procedure. Yeah. Drawing a binary tree and use this tree to represent the cost components in a well-organized way. Then we can derive the answer. Yeah. So that's the idea. Yeah. All right. Let's start. When we start from the root. So that's our goal, s of n. That function, finally we want to find the estimation formula. Yeah. Then, divide and conquer, we split into two branches. Okay? Yeah. In this tree, two branches going down to the two subtrees. So why two branches? Why not 3? Why not 4? Yeah. Because if you look at the original non-recursive inequality, you can see we call the recursive function twice, not 3 times, not 4 times, twice. Yeah. But this last term, the third term, it's not a recursive function call. It is a known expression. It is not unknown. Yeah. So the recursive function at this point, it is unknown. So that's why our branches we only use to cover the unknown expressions. For known expressions, we have a different way to represent it. Yeah, so you will see it. Yeah. So now, so we not narrow down, so we spread, okay? Yeah, because we spread our tree coverage, okay? Yeah, in this visually like this, okay? 2 subproblems we need to solve, okay? So here it means to solve the original problem, it relies on solving 2 subproblems, okay? But there is a third term you need to consider on top of it. So let's put the non-recursive cost here. Yeah, here, so we call it non-recursive cost part. Okay, yeah. So this part, so we put here, we associate with this level, okay, the root level. Yeah. So this non-recursive cost, we need to pay associate. So it is associated with the top root level. Okay, all right. Yeah. Then, yeah. So here, remember, we already paid for it. Yeah. So we pay the cost. Yeah. All right. Then, second level, we need to, branch out to get more branches, more subtrees using the same way. So this time, after we pay some non-recursive cost, we get 2 smaller sub-problems. Yeah. Similarly, this side, after we pay some non-recursive cost, we get 2 smaller sub-problems to solve. Okay? All right. But here you may ask me, how do you know this non-recursive cost is this much? Yeah. It's pretty easy. Yeah. From the original formula, what is the non-recursive cost? Yeah. So you can understand this way. 4/3 multiply the problem size. The problem size is n. So 4/3 times n. Now, here we use the same idea. 4/3 times the problem size. Okay? 4/3, but problem size is n over 3, right? After simplification, 4n over 9. Okay? This side, same way, yeah. 4/3 times problem size, 2n over 3, after simplification, 8n over 9. So pretty straightforward. Yeah. So that's enough. We do not need to draw more branches, although you can, but it's already enough. Yeah. So we get an idea. Yeah. So we get a picture. Yeah. So it's enough for us to further analysis. Yeah. All right. Now, these 2 non-recursive costs, we need to combine. So we pay 2 places, but what is the total cost for this level, this step? Yeah. You add them together, also 4m over 3. So you can see the same as the non-recursive cost in the previous level. Okay? So with this kind of observation, you can expect when you have more and more levels, each level we pay this same non-recursive cost until we reach the very bottom. And then we stop. Okay? We need to stop at some place, right? Yeah. We will see how many levels do we go until we reach the bottom. Yeah. All right. So that number we can estimate. Number of levels log of n. Why log of n? Yeah. So let's look at the size reduction from the branches going down in this way. Okay. All right. And n over 3 every time divided by 3. Okay. All right. Then at the certain level k, n over 3 to the kth power. And this number approximately equal to 1, right? You reach the bottom, right? When that number equals 1, you reach the bottom. Okay? All right. So then you can see you need to stop. Okay? Because you already reached the bottom, you need to stop. Okay? All right. So that means n approximately equal to 3 to the kth power. Okay? So the level number k approximately equal to log base 3 n. Yeah. So here base 3 is not that important, right? Just a constant. Right? So here we just use some abstract base number. Yeah. Okay? Although it's 3. Yeah. Yeah. All right. So we use this log of n to estimate the level number. Then you can see what is the total cost of the estimate. Level number multiply non-recursive cost of each level. So you will get this n log n, constant times n log n. Constant is not important, so that's why we don't need to mention that constant part. Okay, so big theta of n log n. That is our estimate. Unfortunately, this estimate is not what we want to have. This result is not what we want to have. We want to have our goal. We want to have the linear function. Drop that log n. We don't want that log n. Okay? Yeah. So, not good enough. Yeah. So, our solution in this way couldn't give the desired result. Okay? Yeah. So we need to think about it. How to get the desired result. Okay? Yeah. So we haven't finished the solution. Yeah. We need to continue to work on it. Okay? So the question, how to get linear efficiency? Yeah, this is linear efficiency. The function, linear function. Yeah. From n log n function to n function. So we need to improve it. Yeah. So in other words, we need to tighten the estimate. Tighten the estimate. Our estimate is too loose. Not strict enough. If we can tighten it, okay, yeah, so we can get a better estimate. Each level a little better, then the total cost also better, and hopefully get to the linear efficiency. So that is our plan. Okay. So we will do that. We will execute that plan in our last video of this part, E.3.